Hello grade 11s, welcome to this lesson on trigonometric functions, hyperbolas and exponential functions. These 5 functions are functions we deal with a lot in grade 11 and you're expected to know all the little bits and pieces about it. So let's go through them one by one, starting with the hyperbola. Has the formula of y is equals to a over x plus p plus q. In grade 10, we didn't deal with the p, we only dealt with the q, and the q was the asymptote that moved the function up and down. The p then moved it from left to right. Now the a defines in which quadrants it lies. If a is positive, so if a is more than 0, the function will lie in the first quadrant and the third quadrant. If a is less than 0, then it will lie in the opposite 2 quadrants, which is the second and the fourth quadrant. Okay, now these are the most obvious characteristics of a hyperbola, but you're often also asked to find the axis of symmetry. In grade 10, because we were only dealing with q, our axis of symmetry was defined by 2 formulas. Y is equals to x plus q and y is equals to minus x plus q. But with the introduction of p, we need to introduce it into the axis of symmetry. So let's write down those 2 new formulas. The axis of symmetry is defined by, let's just abbreviate it. The axis of symmetry is defined by the formula y is equals to x plus p. Now you'll see it's in brackets. In this case, it doesn't really matter because the x will stay positive. And y is equals to negative, and that's where the brackets matter, because you've got to multiply the p by the negative as well. You need to know these formulas off by heart. They're always going to ask in some odd way the axis of symmetry of the hyperbola, so don't gloss over it. Make sure you know what it is. Now your domain and your range are the same for all of the functions. Your domain is going to be your x values and your range are going to be your y values. Make sure that when you do them, you don't include the asymptotes into your domain or range. So you'll say x is an element of any real number, but x does not equal whatever the asymptote is. And the same with range. Y is an element of any real number, but y will not equal the asymptote. How do we find the asymptotes? Well, let's write down the formulas quickly. The asymptotes are defined by 2 formulas. X is equals to negative p and y is equals to q. When drawing a hyperbola, these are the first 2 things you should look at and plot. Where's your asymptotes? You plot them going down and going across, and then you look at your a value to see which quadrants it lies in. Now we've spoken about the hyperbola, let's move on to the more complex exponential function. The exponential function is defined by the formula y is equals to a times b to the power of x plus p plus q. Okay, there are quite a few variables there. We have an a, we have a b, a p and a q, and we need to know what each one does. So let's start with the a. Now a, in this case, tells us whether it is above or below the asymptote. If a is positive, in other words, if a is more than 0, it means that it will be above the asymptote. Let's abbreviate asymptote to just that. If a is less than 0, then it's going to be below, 1L below. What this means is that if this is your asymptote and a is positive, your exponential function is going to be above the asymptote. If a is negative, then it's going to be below the asymptote. But we're not able to tell which direction the exponential function will be moving in without the value of b. So let's examine the value of b. Okay, so if b is between 0 and 1, it's going to move towards the asymptote. Here is our asymptote. It's going to come up from high and go way down low. Remember, it gets closer and closer to your asymptote, but never ever touches it. So if b is less than 1 and more than 0, it moves towards your asymptote. If b is more than 1, so let's say it's 2 or something to that effect, it's going to move away from your asymptote. Up there, away. Now you'll notice that both of these examples I've drawn above the asymptote because I don't want you to get confused and think that b influences where it will lie. Remember, if a is positive, it's above the asymptote. If a is negative, it's below. If b is between 0 and 1, then it's going to move towards the asymptote. And if it's after 1, then it's going to move away from the asymptote. We still need to talk about what P does and what Q does. Let's start with Q. It's easy to define. Now Q, let's go up. Q represents your asymptote. So if you wanted to write the equation of the asymptote, you would say y is equals to Q. And that would be it, asymptote. Your p-value is there just to move it left and right. Like in other functions, if you're adding to x, it's not going to move to the right as you would naturally think so. It's going to move to the left. You must remember that when you're doing this. Now, domain and range are the same as well. Domain are all of your x values and range are all of your y values. In exponential functions, the domain will carry on forever and ever and ever. If you carry on drawing that exponential function, it will eventually touch all values of x. So your domain is going to be x as an element of any real number. Your range, however, is defined by where your asymptote is and whether a is positive or negative. So draw a quick sketch function of the graph and then you can see where it goes. Let's move on to sine function. Through the years, you've dealt with a number of different functions or a number of different formulas. The first one you've learned about in grade 10 is y is equals to a sine x plus q. Now in this, you'll remember that a defined the amplitude and the direction of the sine function, and q defined where it cut the y-axis. And this year, we've introduced b and p into this equation. Now b has a lot to do with the period of the function. A normal sine function will have a period of 360 degrees. However, if we introduce a value in front of x, it means that we're going to divide the period by b to get the new period. The p will move it from left to right, and remember, whatever we do the opposite. So if we are adding 30 degrees, we're actually going to move backwards 30 degrees. The a defines the amplitude, but it does not mean that it is the amplitude, because amplitude the a can sometimes have a negative answer, whereas amplitude is always positive. Always, always positive. So whatever a is, we need to change it to a positive number in order to get the amplitude. And when we have an a in front of sine x, it means that we're multiplying it, the sine function, by that. Let's do some examples, changing one thing at a time to see what happens. We'll start off with a normal sine function. A normal sine function goes from 0 up to 1 and then down to -1 back to the x-axis. It ends after 360 degrees. Now this would be y is equals to normal sine x. Up to 1, down to -1. Let's change the a value by multiplying it by 2. So y is equals to 2 sine x. Now when we multiply the sine function, it means that we're going to make it that many times bigger. So if we're multiplying it by 2, it usually would have gone up to 1, but it's now going up twice as high to 2. And it usually would have gone down to -1, but now it's going twice as low to -2. The trick with drawing these functions is to draw the function first and then fill in all the values. You get a much better shape that way, and it looks more accurate at the end of the day. Let's do it. So I'm going to start by drawing a basic set of axes, drawing my sine function up and down, and I'm now marking that it goes up to 2 and down to -2. Has my period changed? Well, let's look in front of x. There's nothing in front of x, so that means my period is still going to be 360 degrees. Let's do one now where we change the amplitude and we change the period. So what are we going to introduce to the formula? Yes, we're going to introduce a b value. This means we're going to multiply x by something. Let's choose something simple, something easy to work out. How about 3? Let's see how it looks. Creating some more space. So let's keep it as 2 sine x so that we know it is, or at least 2 sine 3x, so that we know that it's still going to go up to 2 and down to -2. The only thing that's going to change now is its period. I would still draw it in roughly the same way and then fill in the values later. So it goes up to 2, down to -2, but instead of finishing at 360, our new period is going to be 360 degrees divided by, what is our b value? It's 3, giving us 120 degrees. What is the amplitude of this function? Well, we can see the distance that's covered is a distance of 4. So the amplitude is going to be half of the distance covered, which is 2. That's 2 different ways you can find the amplitude. You can either look at the front, or you can look at your function and see which one it's going to be. Let's do something more fancy. We're going to keep 2 sine 3x, and let's add 1 to it. Now when we add 1 to it, it means that we're going to move it. Let's see how it moves. We said earlier that q is the y-intercept. So if we are adding 1 to it, it means that it's going to go up from 1 and then down and then finish again at 1. How far was this? What was the period of this function? Well, it was 120 degrees. Y is equals to 2 sine 3x plus 1. So what is this function traveling to? 120 degrees. What is it going up to? Well, our y-intercept has changed. It is now 1. Before, it was 0. So if it's moved from 0 to 1, it means that 2 has moved, the top point 2 has moved to 3. So that point means that top mark is going to be 3. In the same way, the bottom point was -2, moved up, it's going to be -1. Now we've covered the basics of the sine function. Let's move on to the cosine function, otherwise known as cos. Now, in the cosine function, you've also been given 2 different formulas through the years. You have y is equals to a cos x plus q, and the second one is y is equals to cos b x plus p plus q. Now, generally, we don't combine all of those variables into one formula unless we want to be mean to you. It is possible to do them all on the same set of functions as we've done with the sine function. Now, as you'll remember, the sine function and the cos function are very, very similar. The cos function, however, doesn't start at 0, 0. It starts at its peak, which is at 1. Let's draw an example of what it looks like. So the sine function would usually start down at 0, 0. The cos function is going to start up at the top at 1, go down to -1, and then end up at 1 again. It has a period of 360 degrees in a normal case. However, if we have a value for b, the period will change. So our period calculation is equals to 360 degrees divided by the value of b. Remember that the q value is no longer the y-intercept, because our y-intercept by default in our normal y is equals to cos x function is 1. So it's not the y-intercept anymore. If you know the sine function, you know the cos function. Most things can apply to both. They both have a period of 360 degrees, and they both go up and down forever and ever and ever and ever and ever. So when you learn the sine function, learn the cos function right next to it. Let's move on to the tan function. The tan function is completely different because it has a period of 180 degrees and asymptotes every 180 degrees. Let's look at it. Now the full name for tan is tangent. We have y is equals to tan x. You've also been given a couple of formulas through the years. A times tan x plus q. And then we've got the more recent one of y is equals to tan b x plus p plus q. B influences our period. Remember that in a tangent function, our period is 180 degrees because our asymptotes occur every 180 degrees. So cos and sine had 360 degrees divided by b. Tan likes to be different with 180 degrees divided by b. So our formula for period is equals to 180 degrees divided by b. Now the second thing that's important to note here is that tan's amplitude is infinite. In other words, tan carries on going forever and ever and ever and ever. You couldn't find a piece of paper long enough to draw it on. This is because of the asymptotes. It carries on approaching those asymptotes, but never ever touching. Let's draw an example of what a tan function looks like. We have our set of axes, and the first thing we're going to draw in are some asymptotes. Now remember that these asymptotes happen every 180 degrees, starting at 90 degrees. So we'll put a little 90 in there. And what's 180 degrees later? Well done, it's 270 degrees. The tan function is going to go from the center of these points and travel closer and closer and closer to the asymptote, but remember, never ever touching. It takes quite a lot of practice to get this curve correct, and even as an expert, I struggle to do it sometimes, but I have learned the trick is to start from the middle and go up to the end. Now there is an important point to remember, and it's literally a point over there. That point indicates the point 45 degrees and 1. This makes it easier to move the function up and down. If you know this point, then you can move it up 1 to make it 45 degrees and 2, moving your y-intercept with it. Or moving it down 1 to make it 45 degrees and 0. So learn that point so that you can move it nicely. Remember that when you multiply the tan function, it's a little bit more difficult to draw than a sine or a cos function, because all it becomes is more stretched out. So by plotting that point, you're showing you understand that 2 tan x will reach the point 45 degrees and 2, because 1 times 2 is equals to 2. Let's move on to general solution. We'll create some more space down here. Now, general solution is when you solve for an angle. You've got 3 different functions. You've got your sine function, which starts at 0 and carries on going up and down forever and ever and ever. It carries on going. Then you've got your cos function, which starts at 1 and up and down forever and ever. You get the idea. And then your tan function, which has its asymptotes and doesn't go on forever and ever that way, but does definitely go up forever and ever. It's a never-ending functions. There they all are. Now, if we want to solve for a particular angle, let's say we've been given y sine theta is equals to half, and we need to find out where that happens. We would go along the y-axis and find out where it is a half. So that over there would indicate a half. Now, the answer your calculator is going to give you is that point over there. Let's see what it is quickly. So on your calculator, you would push sine of -1, which is shift sine, and then your fraction is 1 over 2. Close your brackets, and you get an angle of 30 degrees. So this point over there actually happens at 30 degrees. Now what you'll see along the line is that it happens many times, over and over and over again. It's impossible to list all of them though, so we list it in a general solution. You'll see that this point happens again 360 degrees later, and then 360 degrees after that. This point is slightly different because we have 180 minus 30. Where does that come from? It comes from your quadrants. You've got your C, A, S, T, and in A and S, sine is positive, so you'll see it's above the line. S is 180 minus theta, so that point over there is going to be 180 minus 30, which is 150 degrees. Now this point will carry on happening 360 degrees. So when you're asked to solve for an angle, you need to acknowledge all of those other angles that are there, unless they've told you for what domain they want these angles in. So if they've said, find the answers where x is between negative 360 degrees and positive 360 degrees, then you would only give values that satisfy that. If they've said, find the general solution of, then you would give the value of x plus k times 360. The cos is very much the same. Let's take a look. We'll make up a point over here, and we'll see that this line intersects the graph many, many times. And what do you think the intervals are? Well, from there to over there is plus 360 degrees. And from there to there is plus 360 degrees. What do you think that point is? Well, if you look over here, cos is positive in the first quadrant and the fourth quadrant, so this point is going to be 360 degrees minus whatever theta is. The final one is tan. If we were to put a line through tan, we'll see that our general solution doesn't happen every 360 degrees, but rather every 180 degrees. Let's move on to some questions. We'll start with question 1. Question 1 says, the figure shows the graphs f of x is equals to minus 4 over x minus 2 minus 1, and g of x is equals to mx plus k. Before we look at the picture, let's talk about what these functions are. Now over here we have x in the denominator. This means that it is a hyperbola. And in g of x, x just has a coefficient indicating a straight line. What do we know about hyperbolas at this point? We know that hyperbolas have two asymptotes and that they have two parts, either in quadrant 1 or quadrant 3 or quadrant 2 and quadrant 4, depending on the value of a. Let's analyze the function before moving on to the question. Now a is up here at the top. And if you see that minus, the minus actually belongs to the a value, indicating that our hyperbola is going to be in the second and the fourth quadrant. Our asymptotes are indicated by the p-value. And remember, in the formula, it's a plus p-value, so this p-value must be minus 2. And our other asymptote is indicated by a q. Once again, it's a plus q value, so our other asymptote is minus 1. We're not given values for the straight line, which indicates we'll probably have to find them later. The fact that both of these functions are on the same graph means that they'll have points of intersection, and this is dealt with in the next sentence. The two graphs intersect at points A and C. The way we write this if we wanted to be fancy, would be to write g of x is equals to f of x. There are three different ways of asking points of intersection question. They can either ask you to look for points A and C, or to find where f of x is equals to g of x, or to find the points of intersection. Let's take a look at the diagram. Now, as we can see, we've got the hyperbola in the second and the fourth quadrant, and we've got the straight line passing through the hyperbola at 2 points, A and C. They've also indicated another point, B, which lies along the x-axis. This is an x-intercept. The first part of the question says calculate the asymptotes of the hyperbola. Let's take a look at our function again. It said f of x is equals to minus 4 over x minus 2. Remember, minus 2 indicates our positive p value, and minus 1, which indicates our positive q value. Our formulas for our asymptotes are x is equals to negative p, and y is equals to positive q. So if we were to do that, x is equals to negative times by negative 2, which means that x is equals to 2. If they're asking for the asymptotes, they need to have it in equation form. So you need to state the equation of the line passing through that point. At that point, x is equals to 2, and that's what you need to indicate. Let's do the other asymptote. Now, we said the other asymptote was indicated by our q value, and our q value is minus 1. So y will therefore equal minus 1. Now that we've found the asymptotes, we can move on to the next question. The coordinates of the points A and B. If we look at the diagram, B is our x-intercept of the hyperbola, and A is our y-intercept of both the hyperbola and the straight line. Which one would be easier to work with? Well, seeing as our straight line has no values in the formula, it would be easier to work with the formula of the hyperbola. So let's find out what the x and the y-intercept are of the hyperbola. The formula we were given was f of x is equals to minus 4 over x minus 2 minus 1. In order to find an x-intercept, we need to make y equals 0. And in order to find a y-intercept, we need to make x equal to 0. So let's do them fast and do them both at the same time. One on the one side of the page, one on the other side of the page. This calculation should take less than a minute to do. Over here, we'll let y equal to 0 and write out the rest of it. And on the other side, we'll make x equal to 0. Solving for y, we'll start by moving over the negative 1 to the other side, and then we'll put it all over the same common denominator and solve for x. Move the negative 1 over by adding 1 to both sides, and we have negative 4 over x minus 2. Our lowest common denominator is going to be x minus 2, so I'm going to change both sides to be over a common denominator of that, which means on this side, we're going to have x minus 2 is equals to minus 4. What you'll notice is I've dropped the denominators at the same time. This is a skill that you've learned in grade 10, and it's possible to implement it here. Now, we need to get x alone, so we've got to move the 2 over by adding 2 to both sides, making this minus 4 plus 2, which gives us an answer of negative 2. This negative 2 indicates where the hyperbola cuts the x-axis. If we go to the diagram, we'll see that the x-intercept is on the left-hand side of the y-axis, indicating that x would be a negative number. Let's check that we're correct. And there we go. B is on the left-hand side of the y-axis, meaning that x would have a negative value over there. So our coordinate for our x-intercept is going to be B is -2 and 0. Let's continue with the other point. We need to solve for y, so we're just going to add up all our values over here. -4 over -2 gives us an answer of 2 minus 1, which gives us a value of 1. This means that our other coordinate, A, is going to be 0 and 1. Let's check that we're correct. And there we go. A is just above the x-axis, indicating that y is a smaller value than B had on the x-axis. So it is consistent. Let's move on to question 3. Question 3 asks us to find the values of m and k. Now m and k were in the straight line formula, the linear function, where g of x is equals to mx plus k. M is the coefficient of x, meaning that it's going to be your gradient, and the plus value, plus k, will be your y-intercept. If we look at the diagram, we can see that we've already worked out what the y-intercept was in the previous question. And we got the answer 0, 1, meaning that we have the y-intercept of the linear function. Because we've stated that this is the y-intercept of the linear function, we don't have to show our calculations. So it's possible to do this in a very quick, easy way. The next part is finding out what the value of m is. We can do this one of two ways. We can either use a gradient formula and substitute two different points into it, or we could substitute one point into the standard y is equals to ax plus q formula. Personally, I prefer doing the y is equals to ax plus q formula, so that's the method I'm going to use today. We've been given another point, and we'll go and see what it is so that we can substitute it in. The other point we've been given is point C, with a value of 3 and -5. At the moment, what we have is g of x is equals to mx plus 1. We're going to substitute the point 3 and -5, meaning wherever there is a y value, we're going to put in the point -5, and wherever there is an x value, we're going to put in the value 3. We now need to solve for m. Now, you've been doing these types of equations since you were in grade 8, so you should be quite familiar with them by now. You need to move the values over and get m by itself. Let's start with 1. We're adding 1 on the side, which means we're going to minus 1 from both sides to move it from that side. Now, you'll notice at the same time I've multiplied 3 by m to get 3m. m is still not alone, so I'm going to get rid of the 3. Because the 3 is multiplying m, I'm going to get rid of it by dividing both sides by 3, giving me an answer of -2. Now, technically, we have answered the question. We've stated what k is, and we've stated what m is. However, it always makes your teacher happy if you write it in a final formula. So as a last step, I recommend you write g of x is equals to the rest of the equation. Let's show you how to do that. So, as a last step, g of x is equals to -2x plus 1. And congratulations, we've finished question 1. We should now move on to question 2. Question 2 says, the following graph is a graph of f of x is equals to a times b to the power of x, and a cannot equal 0. Before we move on, we need to point out that this is an exponential equation. How do we know this? Well, the x is in the exponent. It gives it away. Remember, parabola has an x squared. Straight line has an x with a coefficient. Hyperbola has x in the denominator. And exponential equation has an x in the exponent. Let's take a look at the rest of the question. It says P, 2 and 144, is a point on F. Moving down, we can see that P, 2 and 144 is a point on F that it's moving down towards the asymptote, which means that B will have a fraction as a value. If we look at the first question, it says if B is equals to 3/4, you see we were right, calculate the values of A. In order to calculate this value, we're going to have to substitute. And in order to find out what one variable is, we're going to have to put values in for all the other variables. Do we have enough values to do this? Yes, we do. There are 4 variables there. We have y, a, b, and x. We've got a value for b, 3/4, and we've got a point, which means we can substitute a value in for y and x. So let's do substitution and solve for a. Let's start with the equation. We have f of x is equals to a times b to the power of x. They told us that b is equals to 3/4. We need to solve for a, and we've got values for x and y. Our value for x is 2, and our value for y is 144. So 144 in the place of y, and 2 in the place of x. Now, not all of us are able to square fractions. It is a relatively easy concept to do. You just need to square the top and the bottom individually. But if you are feeling unconfident, you have a wonderful piece of technology called a calculator, and use it to check your work. I'm going to do it on the calculator just to show you how. So we've got the fraction, 3/4. Close the brackets and square it. You need to have it inside the brackets so that your calculator knows to square both the top and the bottom individually. And your calculator gives you an answer of 9/16. Let's move back to here. Now we have 144 is equals to a times by 9/16. There are various ways we can move on from here. We could either multiply both sides by 16 to get rid of the denominator and then divide by 9, or we could just take the whole fraction to the other side. On this side, we're multiplying by 9/16, and to get rid of it, we have to divide both sides by 9/16. Because you have a calculator, you're able to do this, so let's carry on. So 144 divided by 9/16 is equals to a, and then on your calculator, let's do it. 144 divided by 9/16 gives us an answer of 256. This means that a is equals to 256. Now that we've found the value for a, let's see what the next question asks us to do. The question says, hence write down the equation of f. Hence means you need to use knowledge that you have already. In other words, something that you've already calculated. Hence indicates that you've done a calculation. You now need to use that calculation in this question. In this case, we found the value of a, and we need to substitute it into f of x to have a final equation. It's a very simple problem. Let's go and substitute. Now, f of x was originally equal to a times b to the power of x. We now have our a value of 256 and our b value of 3/4, which was given in the first question, and our x stays open. It says describe the transformation of the curve h if h of x is equals to f of x plus 789. What are we adding to here? We're adding to x, which indicates that we're either going to move left or right. Why? Because our x-axis goes across. If we were adding to y, then it would be going up or down. Now, it's always confusing at this point because natural inclination is if we are adding something, we're going to move to the right. However, that is not true here. If we are adding a value to x, it actually means that we are moving to the left. So if we have to describe this transformation, we're picking up the graph and we're moving it 789 spaces to the left. And that would be your answer for that question. Let's move on to the next question. Question 3 says, draw neat sketch graphs of the functions f of x is equals to cos 3x, and g of x is equals to 3 cos x on the same set of axes for x is an element of between 0 and 360 degrees. This question is wanting to test whether you know what the 3 does in each of these cases. If the 3 is in front of the x, it's going to influence the period. Remember, whatever the coefficient of x is, will divide the usual period. The usual period of a cos function is 360 degrees. So this cos function, cos 3x, will be 360 degrees divided by 3. It will have a period of 120 degrees. That means it's going to go from its up position down and up again in the space of 120 degrees. The 3 times cos x means that it's going to be 3 times the size of a normal cos function. So if a normal cos function starts at 1 and ends at -1, the cos function that's 3 times as big is going to start at 3 times the height, which is 3, and end at 3 times the depth, which is -3. In order to do this question, I would first sketch each one individually and then put them on the same set of axes. So let's do that, and then we'll move on to putting it onto a neat sketch graph. Okay, these sketch graphs are meant to just give us an indication of what they will generally look like. If I'm doing it, I'll start with a tiny little sketch that starts at 1 and goes up again, and then I'll fill in all of the values. Let's start with f of x, where cos is equals to 3 times x. As we said just now, the period is therefore going to be 360 divided by 3, which is 120 degrees, meaning that at this point over here, it ends at 120 degrees. Has cos been multiplied by anything? No, it hasn't. So it's still going to start at 1 and go down to -1. This intercept over here is at 30 degrees, and this intercept over here is at 90 degrees, meaning that this point over there is going to be at 60 degrees. Now this just helps us to later on put it all on the same set of axes. What we can see so far is that our intervals on the neat sketch graph is going to be 30 degrees each time. Now that we've drawn a rough sketch of that, let's complete it for the full period that they wanted. They wanted drawn for the domain of between 0 and 360 degrees. At the moment we have it drawn up to 120 degrees. Let's continue the pattern. If it goes on, it's going to go down again and up again. Now we've completed another cycle that goes until 240 degrees. And down again and up again. This would be where it ended at 360 degrees. This is by no means a neat sketch graph. This is just the pre-sketch to putting it all on the same set of axes. With these kinds of questions, you get marks for your intercepts and your shape. So it's important you get it right before you put it on. Occasionally there'll be a mark allocated to neatness, but you shouldn't rely on this. Rather get your intercepts and your shape correct. Okay, we need a bit more space to draw the next one, so I'm going to draw it down here. The next one was 3 cos x, indicating that it would go 3 times as high. Once again, I draw a basic sketch of a cos function and then fill in the values 3 and -3. This will go all the way to 360 degrees. And we'll have intercepts at 90 degrees and at 270. Now that we have both of these basic functions drawn, we can draw them on a neat sketch graph. And here we have our set of axes. Now we know that on the y-axis we're going to need 3 units up and 3 units down. So let's label them in 2s. We have a 1 over there, 2, and a 3. And going down, 1, 2, and 3, and of course these are all negatives. We said we were going across in 30 degrees. I'm just going to mark every 90 degrees. That's going to be 90. 90 degrees later will give us 180. 90 degrees after that will give us 270. And another 90 degrees will be 360. The easier function to draw is going to be 3 times cos x, because it's just a once down and once up. There's not lots of little up and down, up and down, up and down, up and down. So I'm going to start with that, and we'll draw it with pink. It starts at 3. I'm going to indicate a few points to make it easier for myself to draw. It's going to go down to 90, then it's going to go down to -3, up to 270, and the last point is at 360 and 3 degrees. Let's draw the curve. And it goes up again, passing through 270, and lastly curving around to a gentle curve at the top. Now, as you can see, I've got the general shape correct, and it's going through all the right intercepts, so I'm going to get full marks for that part of the question. We now need to plot cos 3x. Remember, this has a period of 120 degrees, so it's going to go up and down 3 times in the same amount of space. Let's look at it. For this function, let's plot it in green. It's going to start at 1, then at 30 degrees, cross through, and then at 60 degrees, go through again. Now what you can see is it goes up and down quite quickly. Remember, these points are just to give you a clear guideline of where to draw it. So we're going to go down, and then we're going to start curving up round about over here, and then follow through and start curving down again. Let's fix that line quickly and go all the way through the point and down and through. Okay, we've now drawn both cos functions. It's important to label your functions so that your teacher knows which one you've drawn where and that you understand it. Let's go back and check the names quickly. F of x was cos 3x and g of x was 3 cos x, so the g goes up to 3. In other words, our purple one, or our pink one, is g, and our green one is f. Let's move on to the second part of question 3. The second part of question 3 asks us, hence determine the values of x for which g of x is more than or equal to f of x. In order to do any of these questions, you need to understand what an inequality is. An inequality is a way of listing a whole lot of values. So you can say that they're all going to be above 3, or whatever it is. When they start talking about it in terms of functions, they want to know which function is above or below the other function. In this case, they're asking, g of x is more than f of x. In other words, where is g of x on top of f of x, and this would be the bottom. Let's take a look at our graph. So g of x must be on the top, and g of x is our pink one. Now we can see that the pink is on top of the green before 90 and then after 270. Because this function has only been drawn from 0 to 360, we're not actually concerned about what's happening on either side of that. We only want to know the answer from 0 to 360. So we're going to say that this happens before 90 degrees and after 270. Writing this down, we need to use an inequality as well. They want to know more than or equal to. Now this happens between 0 degrees and 90 degrees, as well as between 270 degrees and 360 degrees. You see there are 2 marks allocated and there are 2 inequalities given. The next question says g of x is greater than f of x. Now there's a very slight difference between these 2 questions. The first question said g of x is greater than or equal to f of x, and the next question, g of x is just greater than f of x. This means we don't want to know where they're touching. We want to know when g of x is distinctly above f of x. So it can't touch, it must just be above it. If we go back and look at our function, we can see where this happens. We'll see that they touch at 90 degrees, which means that the values for x will be less than 90 degrees, but not equal to 90 degrees. The same thing happens at 270 degrees. Now you'll see still at 0 degrees, g of x is above f of x, so it's still going to be equal to or more than 0 degrees. Let's answer the question. So, where g of x is greater than f of x, it happens at 0 and at 90. But remember, 90, they touch each other, so it's just less than 90. It also happens between 270. Once again, we can see that it touches at 270, so it can't be equal to 270. Remember that line underneath the inequality indicates that it can also equal 360. The last of these sets of questions asks for where f of x is greater than g or equal to g of x. Let's look at the functions. F of x was the green one, and it means where f of x is on top of g of x. And we can see that that happens between 90 and 270. So we're going to write it as an inequality again. Let's go back to green. And it happens between 90 degrees. Once again, they don't mind that they touch, so we're going to put the line underneath to indicate it can equal 90 degrees, and it can equal 270 degrees. Now you'll see with this question, there's 1 mark allocated to it, and with the other 2 questions, 2 marks. The mark generally indicates how many inequalities they'll have. With these questions, most people forget how to answer them, so it's important you practice them on a regular basis so you remember when they start showing inequalities, they want an inequality as an answer and they want it in reference to the x-axis, so the degrees that are happening on the x-axis. Let's see what the next part of the question says. The next part says, write down the values of x for which 1 over 3 cos 3x minus cos x is equals to 0. They've been a little tricky here. They've got one function that looks slightly like something you've seen before, but it's got the third in front of it. And then the other function, which just looks like cos x. So we need to play with them a little bit, see if we can get them to look like things we've seen before, and then as a result, solve them. Remember, whenever you're playing with equations, the same rules apply. As long as you follow BODMAS and whatever you do to the one side, you do to the other side, you'll be okay. Don't be scared to play. If you do nothing, you can't get any marks, so you might as well play with it. Let's look at it. Well, let's get ourselves some more space and work it out. They said 1 over 3 cos 3x minus cos x is equals to 0. The one part of this equation that really bothers me is the fraction. Now, fractions are meant to be our friends, and we're meant to be able to work with them, and most of the time we can. But why do it when you don't have to? So the way we're going to get rid of it is we're going to multiply the whole equation through by 3. This means that we multiply every single term in the equation, including the 0. Let's do it. So 3 times a third cos 3x gives us an answer of cos 3x. Minus times 3, minus cos x times 3 is going to be minus 3 cos x, and 0 times by 3 gives us 0. What do we see now? We see the 2 functions we've been dealing with the whole time. They wouldn't put this part of the question into this question if they didn't want to link the 2 up. Let's put the 1 function on the other side and see what happens. So we have cos 3x is equals to 3 cos x, and what do you know? They're looking for points of intersection. Now we don't need to solve this. We can just go to our graph, and we see that the points of intersection happen at 90 and at 270 degrees. So there's no need to solve it. We can just write down our answers. X will be equal to 90 degrees, or x will be equal to 270 degrees. And that's it for that question. Let's move on to question 4. Question 4 says, draw neat sketch graphs of f of x is equals to cos x minus 30 degrees and g of x is equals to sine x plus 30 degrees. Now before we get onto the domain that they want it drawn for, let's talk about the adding and the subtracting of values. If we're adding a value to x, naturally we're going to want to move to the right. However, don't give in to the temptation. You need to move to the left. So always do the opposite of what you naturally want to do. So in the cos function, where we're subtracting 30 degrees, move to the right. Little r for right. And in the sine function, when we're moving 30 degrees and we're adding it, we're going to move to the left, an L for left, just to remind us. Now it says on the same set of axes for where x is between negative 120 degrees and 210 degrees. They haven't made this easy for us. They've moved things around, and now they want it from a funny angle to another funny angle. So we're going to start by first drawing sketch graphs of them, not neat ones, just a little rough one to give us an idea of intercepts, and then we're going to move on to the neat one. Let's start with the cos function. Now cos, we're moving 30 degrees to the left. Let's give ourselves some space. A normal cos function, so in other words, what we're not drawing, will look something like that. It'll go up to 1, it will go down to negative 1, and it will intersect at 90 degrees and at 270. Now they are wanting us to move 30 degrees right, which means that all of those points are going to move 30 degrees to the right. Let's draw a new set of axes. And instead of going through at 90 degrees, we're now going to go through at 120 degrees, because 90 plus 30 gives us 120 degrees. And instead of going through at 270, we're going to go through at 300 degrees. Now this also means that our top point is also going to move across to 30 degrees. So our peak is now at 30 degrees, and the lowest point will now move over to 210 degrees. There is our lowest point. So there we go, a basic sketch function of what's going to happen. Now in the original question, they only want it from negative 120 degrees to positive 210 degrees. So this part that's over here, from 210 to 300 degrees, is not actually relevant. I'm going to get rid of it, otherwise I'm going to draw it later, and that'll just confuse me. So I'm going to 210 degrees. I now need to go back down on the other side. Usually, a normal cos function would go down at negative 90 degrees, or meet the x-axis at negative 90 degrees. Because we're adding 30 degrees to that, it's now going to go down at negative 60 degrees. So it's going to come down, go down somewhere over there, and it's going to reach its lowest point. It would have been lowest point at negative 180 degrees. It's now going to reach its lowest point at negative 150 degrees. Carry on going down over there at negative 1. It's not the most accurate graph, but it'll do. It's just a sketch. We don't want it to go all the way to 150 degrees. We only want it to go to 120 degrees. So once again, I'm going to get rid of this and show that it doesn't go all the way to 1. So let's make it go just short of it, and here is -1. That goes all the way to -1. That's our basic cos function that we need to sketch. Now let's move on to the sine function. Remember, the sine function has exactly the same shape, only it starts in a different place. Let's look at the basic shape and then move it according to what they want. Now the basic sine function, let's just label this quickly. That was cos x minus 30 degrees. And our sine function is going to be sine of x plus 30 degrees. In other words, we're moving 30 degrees to the left, 30 degrees backwards. Our usual sine function starts at 0, goes up to 1, and goes back down and up again. This sine function will not start at 0. It's going to start 30 degrees further back. So if we draw a set of axes over here, instead of starting at 0, it's going to start at -30 degrees. That means when it would have reached the top at 90 degrees, it's now going to reach the top at 60 degrees. So it's going to go up, 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 and reach the top. And instead of intersecting the x-axis at 180 degrees, it's now going to intersect it at 150 degrees. So then it goes down. It's going to carry on going forever and ever. 90 degrees later will give us the answer of 240 degrees. So it reaches its lowest point at 240 degrees, the lowest point being -1. They want it until 210 degrees. So do we need to draw it all the way there? No, we don't. But what we do need to remember is that it's not going to end at 1 when we do it. So let's carry on this side. We've only drawn it to -30 degrees, and we need to draw it further all the way to -120 degrees. Lucky for us, that works out quite nicely because that also happens to be the lowest point for this at -1 degrees. At -1. And there we go. We have a sketch of cos x minus 30 degrees, and we have a sketch of sine x plus 30 degrees. It's going to be g of x is equals to sine, and that means that this other one is f of x. Let's put them on our sets of axes. Now, our set of axes we've got to set up before we plot it. So we need to know where all the intervals are going to be. We need to decide on the intervals, and we need to decide how high or how low we're going to go on the y-axis. Our functions both reach a maximum point of 1 and a minimum of -1, and we have a domain set out already. We know that we need these intervals to be every 30 degrees in order to plot an accurate graph. So let's label our axes. And here is our set of axes. I'm going to make it a little easier on myself and label this point over here 1, meaning that this point is half, and this -1. So this is our y-axis, and here's our x-axis, and we said we were going in 30s. Now I'm only going to label every third line, meaning that this is 90 degrees. It just makes it less cluttered when you do it. 90 degrees, the next one's going to be 180 degrees. And after that would be 270, but we don't actually need to go all that way. We just need to go to that point over there, which is 210 degrees. On this side, this would be -30, -60, -90 degrees. And we're going to end over there, which would represent -120 degrees. Let's stick with the colors we've had previously. We used pink to plot f of x is equals to cos x minus 30 degrees. And let's start with a point, 30 degrees and 1. So at 30 degrees and 1, we'll make a mark. From here it's relatively easy because we're going to go down, we're going to go up. So let's follow the curve. At 120 degrees, which is over here, was the x-intercept, and then it went all the way down to -1 at 210 degrees. Now over here, it's going to go through the axis at -60 degrees, and then carry on going. Remember we said that it wouldn't quite reach -1, so I'm going to put a little dot there to remind me not to go all the way to -1. Drawing in the curve, and there we go, and down on the other side, and it reaches -1. Phew, we've drawn the cos function, and it's now time to move on to the sine function. Remember, you need to label the functions as you go along, so let's just check that we've got the labels right. For the cos function, it was f of x, so this we'll label f, and then for the sine function, we'll use green, and it is labeled g of x. If we look at our sketch, we'll see that we went to 1 at 60 degrees. So that's where I'm going to start over here. Go to 60 degrees and go up to 1. Now this means that 90 degrees later, at this point, it intercepts the x-axis. And 90 degrees before, it intercepts the x-axis. It also means 90 degrees after that, it goes through at 1. And it didn't go all the way to 1 on this side, so I'm putting a little dot over there to remind myself not to go all the way down. Let's draw it in. So here we go, that's a relatively good curve, and not quite all the way to 1, and let's label it G. Okay, I'm quite pleased with that. We've now labeled the axes, we've drawn the graph. We now need to make sure that we've explicitly stated where there are x-intercepts and y-intercepts, because that's what you get marks for. Let's go back to our graph. So we went through at -60 degrees. Let's label it. -60 degrees and 0. And we went through at 120 degrees. So let's label that point. 120 degrees and 0. We also need to label the sine function, where it went through at -30 degrees and 0. It went through at 150 degrees and 0. And there we go, we've done quite well. Let's see what the rest of the question asks for. The rest of question 4 says, hence solve f of x is equals to g of x algebraically. Now remember that when they say something like this, they're looking for a point of intersection. They've made the two functions equal to each other. So we need to then make the two functions equal to each other. That means that our cos function will equal our sine function, and we'll have to play with it to get it to work. I can see that we're going to use general solutions here, so I hope you've been revising it. Let's move on. So our two functions are cos x minus 30 degrees and sine x plus 30 degrees. Let's make some more space down here. So cos of x minus 30 degrees is equals to sine of x plus 30 degrees. Our first problem is that cos and sine are not the same ratio. However, if you remember back to your trig section, you'll remember that you can change sine to cos and cos to sine by using 90 minus. So let's do that. Let's change sine to cos. We're going to do that. Let's leave cos the same on this side. And then on the other side, we're changing sine to cos, and in brackets, it's going to be 90 minus the original angle, which is x plus 30 degrees. And let's multiply and add what we can on that side. Cos 90 minus 30 is going to be 60 degrees minus x. And on this side, we've done nothing with cos. At this point, there's not much more we can do with what's in the bracket, so we're going to move on to general solutions. We're talking about cos, and it's positive in this case. So we're looking at quadrant 1 as well as quadrant 4, if you remember your CAST diagram. So we're going to start with working in quadrant 1. Remember, you've got to add k times 360 to indicate that this is a general solution. Let's start. Give ourselves some more space. So we're working in quadrant 1, where cos is positive. That means we're going to have x minus 30 degrees. Let's go up a little. There we go, x minus 30 degrees is equals to, and our other angle is 60 minus x, and we're going to add k times 360. If it makes you feel better, we can put the brackets there to indicate that it comes straight from there, but it really doesn't make too much of a difference. We now need to move the 30 degrees over to the other side and the x over to the other side so that we can have degrees and x's separate. So we move the x, it was negative over there, so we're adding x to both sides where it becomes positive over here, x plus x, and the 30 degrees is being minused here, so we add 30 degrees to both sides, 60 degrees plus 30 degrees plus k times 360. And we have our next line of 2x is equals to 90 degrees plus k times 360. We now need to get rid of the 2. We've got it multiplying x, which means we're going to divide everything by 2. 90 divided by 2 gives us 45 degrees. The k stays the same because the 360 will absorb the damage. 360 divided by 2 gives us 180 degrees. K times 180 degrees. Now we need to find out what values suit the domain that we've used and we've drawn the function for. So between that negative 120 degrees and 210 degrees, what values does x satisfy? We're going to do this by substituting integers into k to find that. Remember, we only substitute integers into k. We don't do any fractions and we don't do any decimals. Let's start with 0. If we substitute 0 into k, it means, let's do it in a different color, it means that we're going to get 45 degrees plus 0. Does it fall between negative 120 degrees? Remember, x is an element of negative 120 degrees and positive 120. Does 45 degrees fall between those? Yes, it does. So x can therefore equal 45 degrees. Now let's multiply k by 1. 1 times 180 plus 45 degrees. Let's use the calculator. 45 degrees plus 1 times 180, close brackets, will give us an answer of 225 degrees. Does 225 degrees fall into this bracket? No, it doesn't. So we don't include that in our answer. Let's try negative 1. Clear that. 45 degrees plus negative 1 times by 180 degrees gives us an answer of negative 135 degrees. Does it fall into our domain? No, it doesn't. So from quadrant 1, we only get one answer of x is equals to 45 degrees. Now remember, on your graph, this will represent where the functions intersect. Let's see what happens in quadrant 4. We'll make some more space for ourselves. And back to green. In quadrant 4, now in quadrant 4, it is the formula of 360 minus. So we're going to have x minus 30 degrees is equals to 360, and this is where it helps to have the brackets, x minus 60 degrees. I'm sorry, that's my mistake. It is 60 minus x degrees. Always good to check your work as you go. 60 minus x degrees plus k times 360. Remember, we use the 360 because it is a cos function. Now we need to multiply out what we can and get all of the x's together. So we have 360 minus 60 degrees will give us 300 degrees plus x plus k times 360. Now we need to bring the x's together, and I see a problem that's about to happen. We're adding x over here and we're adding x over there. If I want to get rid of the x on this side, I'm going to subtract x from both sides. This is going to result in there being no x's left in the equation, which means that the solution just doesn't exist in quadrant 4. So there's no solution in quadrant 4 for this problem, meaning that our only answer is x is equals to 45 degrees. You do get a mark for writing no solution, so don't forget to write it down. It's an easy mark if you've done the calculations. So we write no solution. And that brings us to the end of the questions. Remember grade 11s to study what the values of a, b, p, and q do to every single function, starting from linear functions right through to tan functions. Remember, you need to label your intercepts and your asymptotes and know how to read your domain and range. Also, remember when to use your general solution or to give just a straight answer. The last tip I have is to study, to practice, and don't panic. Good luck, grade 11s. Goodbye.